Welcome to example 7. We have a grandfather clock that keeps perfect time at a location where the acceleration due to gravity is exactly 9.8 meters per second squared. When the clock is moved to a higher altitude, it loses 80 seconds per day. Find the value of the acceleration due to gravity at this new location. So let's write down some things that we know. So we know that it keeps perfect time. So it's a grandfather clock, I would assume, and perfect time would be 1 second. And the acceleration due to gravity at that location is 9.8 meters per second squared. Now, we're told not what the new period is, but you have to kind of figure it out for the information they give you. They tell you that you move to a higher altitude, and t equals 2 pi square root L over g. So if you move to a higher altitude, hopefully you recall that g will get smaller. So as g gets smaller, the period will get longer. So basically, the period at the higher altitude location, will be longer because it's losing time per day. So let's find out what that new period would be. We know that it loses 80.0 seconds per day. Let's find that change in time. That's 80.0 seconds per day. So we have 1 day, but we need to convert that to seconds. There are 24 hours in 1 day, and then there are 60 minutes per hour, and then there are 60 seconds per minute. So that will give you 80.0 seconds divided by 86,400 seconds. So the difference in the periods of the pendulums at different locations will be 9.259 times 10 to the power negative 4 seconds, or you could say 0.926 milliseconds. So what will be the new period now? Well, the new period will be slightly longer because it has a smaller acceleration due to gravity and because it's losing time per day. So it's 1 second plus 9.259 times 10 to the power negative 4 seconds. So that will give you a period of 1.000929 seconds. Now, we're not told the length of the pendulum. I suppose you could solve for it, but it's not necessary. You could really just make a relationship, a proportion between these two formulas. Meaning there's one formula here for the original location, and then under the new higher altitude location, the new period would be given by 2 pi square root L divided by g prime. So we're going to assume, obviously, that the pendulum length hasn't changed. So now if we do a ratio of these two equations now, so if we take equation 2 and divide it by equation 1, we're going to get t primed over t is equal to 2 pi square root L over g primed divided by 2 pi square root L over g, which will basically come out to be g divided by g prime. So therefore, t period, the new period, well, we could solve for g now. The new acceleration due to gravity will be now the original acceleration due to gravity of 9.8 times the period originally it was at, divided by the new period, and all of that squared. So let's go ahead and substitute our numbers in. We have 9.8 meters per second squared divided by the period of 1 second, and then we have 1.000929 seconds, all that squared. And that gives you a new acceleration due to gravity of 9.78 meters per second squared. And that's it for example number 7.